talk will be about the paper that one Ariel Feller will start, I guess, and then Nathan Studebat will continue. And it's about the first bidirectional heuristic search guaranteed to meet in the middle.
Okay, thank you very much. So you see the title of the paper. Unfortunately, the first author of this paper, Robert Holty, could not make it to AAAI. So the talk will be given by myself and by Nathan.
Will you meet in the middle?
We will meet exactly in the middle. Everybody knows some very known background about unidirectional search. Nodes are ordered in an open list according to a cost function. If our cost function is Fn equals to Gn, where Gn is the shortest known path from the initial state to n, then we have a best first search or Dijkstra's algorithm in case the graph is weighted, and this is what breadth first search does. If we add a heuristic, an admissible heuristic, which is a lower bound estimation on the cost from n to the goal, then we get to the A star algorithm, which actually looks like this. And everybody knows that there are nodes that are expanded by breadth first search that are not expanded by A star because the heuristic pulls them away. What happens when we move to bidirectional search? Okay, so if this is breadth first search, if the optimal solution cost is C star, and the domain is growing exponentially, then the size of the search tree is B to the C star. When we move to bidirectional search, then we have the luxury of only working in these two small yellow circles, and now the search size is 2 times B to the C divided by 2, and this is an exponential reduction, and this was the main motivation to perform bidirectional search because of this significant reduction in node expansion. However, the main challenge is what happens when we add heuristics to both searches, to unidirectional search and to bidirectional search. Can we keep this significant reduction in node expansion? Turns out that 50 years of research have been done. Many researchers tried to work on bidirectional heuristic search, in fact, including ourselves a few years ago, but the general thing we can say is that there was no lasting success and that bidirectional heuristic search is not broadly used, especially outside of the research community, and no one could really significantly achieve the same reduction with heuristics. And moreover, there was no comprehensive theory to explain what is going on. Now, there was a paper by Barker and Korf last year in AAAI, and they suggested a few claims about when and why bidirectional heuristic search will work or not. There was a hidden assumption in their work that the searches frontiers meet in the middle. But there was no known bidirectional heuristic search that was guaranteed to meet in the middle, so this inspired us to actually look for such an algorithm with this guarantee. Let's look a little bit about the challenges of devising a bidirectional heuristic search algorithm. So the first challenge is that the frontiers should meet. You know, they might just pass each other. And in fact, this was a historic engineering task in many occasions, and whenever this happened, when they met, finally they were very happy. You see the pictures here. But for a bidirectional heuristic search, many of them actually guaranteed to meet, especially if the domain is finite, then the frontiers are guaranteed to meet at some point. Now the next challenge is about optimality. What happens if your if your frontiers meet not on the optimal path? So what most bidirectional heuristic search algorithms do, they continue to expand more and more nodes until the frontier gets larger and they can prove that the solution they have is optimal. Next challenge is where do they meet? And this is where we come in. And we will present now the first bidirectional heuristic search algorithm that is guaranteed to meet in the middle, and I will explain why is this such an important attribute. So our main contribution in this work is, first, we have a novel expansion ordering rule that was never used before in bidirectional heuristic search. People usually just use the regular G plus H rule. We have a new stopping condition, and most importantly, we have new ways of doing analysis and starting to really understand what is going on by all the searches around. Okay, so how MM works? We have a new priority rule. Nodes are expanded by the following priority. PR of n is the maximum of two options. Option 1, the regular G plus H. Option 2, 2 times G. Whatever is larger, this is a priority of a node. You can write it a little bit differently, so PR of n is Gn plus the maximum between G and H. Okay, so now that every node has its priority, we choose a node on either side with the minimal PRN. Once we generate a node, we look at the opposite frontier to see if there is a match with the opposite frontier. If there is a match, then we have found the path. We keep track of the best known path, because the cost of U, and when we can stop when U is smaller than or equal than a lower bound on the optimal solution. And in our paper, we have quite a few lower bounds, and we compare to all of them. So we are guaranteed that our solution is optimal. In fact, the last 3 lines is rather similar to regular or to previous bidirectional search algorithms. Okay, so the main point of our paper is this lemma. MM never expands nodes with Gn larger than C star over 2. As a result, or we never go beyond those 2 yellow circles. As a result, the frontiers must meet in the middle. Now let me give you a sketch of this proof. So let n be such a node outside these 2 circles with Gn larger than C star over 2. What is the priority of this node? So there are 2 options. In both cases, we take Gn, which is larger than C star over 2, and we add something that is also larger than C star over 2. So overall, the priority of any node outside the 2 circles is larger than C star. However, we always have a node, X, which is on the optimal solution, and according to the priority, its priority will be smaller than or equal to C star. Which means our algorithm will always keep on expanding these X nodes until we find the optimal solution and halt, and no such node n will ever be expanded. So, of course, the main result is that we actually guarantee to meet in the middle, but what is equally or even more important is now we have an upper bound for mm. This 2 times b to the c divided by 2 is now an upper bound for our heuristic search also, because we will never go outside these circles. Furthermore, this allows us now to provide a deeper analysis on a per-region basis of what is going on, as Nathan will show in a few minutes. We also have a simple variant of MM called MM0 without a heuristic, and if you look closely on the map, then the priority converges to actually be prioritized by Gn. To summarize, intermediate summary on the high level of what's going on, this is breadth first search, this is A star, this is MM0, this is MM. I will let Nathan now to continue.
And if we look at this picture, it seems like it's sort of an obvious abstract picture, but what we're going to see is in this picture, in many cases, is actually not what's going on. So what I'm going to show you here is a region-based analysis. We're going to look at how the different algorithms work. We have a strong mathematical background behind this, but for here, I'm just going to show you some nice pictures so you get a visual intuition of what's going on. We'll spend a very brief amount of time on the experimental results. So we're going to do 3 analyses. The first is going to be a breadth first search versus MM0. And this analysis works on any state space. It doesn't have to be exponential or anything else. So what we're looking at here is that a breadth first search is going to expand all states out to a cost C star. And these would be the states, or representative of those states. If we're looking at MM0, we do all states out to C star over 2. And what we really want to do is compare these sets. What is the difference between these sets? So the orange states here are the ones that are expanded by both algorithms. And the difference really is what is in the red state for my breadth first search, what are the yellow sets of states for MM0. To make this really practical, we'll show an example on a 2-dimensional map. And the start state is at the top, the goal state is the bottom. And this is just the states as a breadth first search expands from the start working out towards the goal. And this is polynomial, not exponential, so some of the things here won't always be 100% applicable to exponential domains, but it gives a good intuition here. So here's our search. This is exactly the red states we were talking about previously. We can do the same thing with MM0, do our bidirectional search. The searches here are going to come and they're going to meet in the middle. And as they do this, then this is going to define for us the yellow states that we were looking at before. And so now we can ask the question, well, what is the union of these sets? And we see these orange states are the ones that both algorithms are forced to expand. And if we want to know which one is going to be better, we have to compare. What is the difference between the red and the yellow here? And it ends up in this case that there's slightly more red states than there are yellow states, but there's a very interesting property in this sort of brute force search that we can show, which is as the problem gets harder and harder, the set of yellow states here shrinks. And to demonstrate this, I'm going to take my goal state and I'm going to gradually move it down, and I'm going to animate what happens to the set of yellow states as this occurs, and to the red states as well. And you see, as I go to sort of the hardest problem I can create in this map, the set of yellow states entirely vanishes. So on the hardest problems, it is always the case that a bidirectional search will dominate a unidirectional breadth first search. The second case we want to look at is a heuristic search. Here now we're going to compare A star and MM. So this is our breadth first search. When we add a heuristic, we can prune away these purple states. We're left with the red states sitting in the middle here. The same thing with MM0, I add a heuristic to it, and I get to prune away all the blue states. I'm left with the yellow states in the middle. So going back to our abstract diagram here, we want to analyze the case where I have a strong heuristic. A strong heuristic is generally very accurate, at least up to halfway through the state space. And so if we look at the left part here, where the start is, MM and A star in this region, it ends up that the pruning that they do here will be identical, and there's no difference. So we can completely ignore this set of states in our analysis. We're assuming a strong heuristic, so in this red region for A star, the distance here is at least C star over 2. So the heuristic is actually going to be doing a fair amount of pruning within that region, and this region will be fairly small, again, only with a strong heuristic. What's really interesting, though, is what happens in this other side over here, this other set of orange states, on the right-hand side, where both MM and A star are going to be analyzing that region, and we want to show what happens here, because this is one of the non-intuitive results that we find. So we zoom in on this case, and I want to ask, for some arbitrary node here, how are we going to do pruning with our unidirectional and our bidirectional search? So A star comes along this really long path from the start on the left-hand side and reaches this node. To be able to prune this node, it actually only needs a relatively small heuristic value because it's starting to get really close to the goal. So it's very common to see A star with a good heuristic will prune this state, and the set of states that are expanded in this region will be relatively small. MM, on the other side, reaches this state via a very short path, which means that it needs a very large heuristic to be able to prune this state. So MM is going to have a very hard time pruning this state, and in general, we're going to see in this region that it's much more likely that A star prunes many states and MM does not. So if we look at this picture, what we see, the orange states are ones that are expanded by both algorithms, and yellow is what's expanded by MM, and A star is what's expanded in red here. And so we see that MM is actually has much better performance, or sorry, has much worse performance in this example when we have a very strong heuristic. When we look at the example here now, so that's a strong heuristic, let's go look at the case when we have a very weak heuristic. And here we're going to compare MM without a heuristic to MM with a heuristic. Now in A star, what we're used to is adding a consistent heuristic and getting a stronger consistent heuristic never causes us to do more work. But what we're going to see here is as we take no heuristic and we add a very weak heuristic, we'll actually perform worse. So here's the states that both of these algorithms might expand. And we have this picture, which we think maybe MM is going to do, where we get this nice sort of going right to the middle, and our heuristic is helping us a lot. But when I have a weak heuristic, it's actually the opposite thing that happens. The searches go in the opposite direction, and the reason for this is an inaccurate heuristic tends to have local minima with low heuristic values that are a long ways from the start of the goal. So my search starts out in the wrong direction, and the search actually proceeds from the back half of this region towards the front half of the region. What's going on here is this is where the most accurate heuristic values are. They're close to the goal, close to the start, and that's right at the point where we meet. So the search actually does everything it can to avoid finding the goal when we have a weak heuristic. Now, to compound that issue, so we're still going to meet in the middle, we're still bounded in what we're going on, but we have a new termination rule for MM0 that allows us to terminate an epsilon earlier. And what that epsilon means is we can actually avoid a majority of the states at the very fringe of one of these searches. And so what we see is MM0 is guaranteed in these sort of cases to be no worse than MM. Did I get that right? MM, yeah. And so if you take a look at the paper, then you'll see the details of how that works. So this results in three conjectures. It says with a strong heuristic, we're going to expect MM to do well. With a weak heuristic, we expect MM0 to do well. And then in these in-between cases where we're going to see MM doing well. So we have two sets of experiments here. The details of these are not important. What's important is the trends as we vary the heuristics and vary the problem difficulty. And we're only going to look at nodes expanded here as a proxy for these results. So what we see as we make the heuristic more accurate, we get a transition from MM0 to MM to A star. This is in the pancake puzzle. In Rubik's Cube, as we make the problems more difficult but keep the heuristic fixed, we see a transition from MM to MM0. When we use a stronger heuristic, then the transition is from IDA star to MM to MM0. So this is an algorithm, MM, that's guaranteed to meet in the middle. It opens up a completely new analysis of algorithms, these bidirectional algorithms, and explains a lot of what's going on in the performance. But there's lots of new questions about how we can build different heuristics, what are the variants that we can do on these algorithms, and deeper comparisons between existing algorithms. But this represents a big jump in our understanding. Thank you for coming. We'd be glad to take questions.